My little son, why are you always playing this game?
But Dad, I just started playing.
You're a liar. You should study more. Come on. You should get A, you should get 4.0 GPA. If you still playing this game, I will kick you out of my house. Go somewhere.
Oh my God, this is too much pressure.
Wait, we are not talking about that kind of pressure. Today we are diving into a different kind of pressure in ideal gas. In this video, we will explain what an ideal gas is, explore the kinetic molecular theory, understand the ideal gas law equation, and finally, discover how this connected to a famous Cambodian legend involving clever physics and tradition. What is ideal gas? An ideal gas is a collection of atoms or molecules that move randomly and exert no long-range force on each other. Each particle of the ideal gas is individually point-like, occupying a negligible volume. After we know what ideal gas is, let's take a look at some theory related to ideal gas, or we could call kinetic theory. As you can see that, when we pump gas into a container, molecules begin to move randomly at different speeds. Therefore, the principles of the kinetic theory are as follows. Many molecules, random motion, variety of speed. Size of molecules is small compared with the distance between them. Molecules obey the law of Newton's mechanics. No force between them except when they collide. Collision with other molecules and the wall are perfectly elastic, which means no energy loss. All molecules in the gas are identical, which means they have the same property. Once we understand kinetic theory, we can move to the ideal gas law equation. You might be familiar with this equation when you study in high school. PV equals to nRT. P is pressure in Pascal, V is volume in meters cubed, N is number of mole, R is the universal gas constant, which is equal to 8.31 joule per mole Kelvin, and T is temperature in Kelvin. After understanding an ideal gas law equation, we will now explore in detail the interrelationship between its variables, examining how change in one parameter influences the other under various conditions. First law is Avogadro's law. Avogadro's law tells us that the equal volumes of gas at the same temperature and pressure contains equal number of molecules. That means volume is proportional to the number of moles.
Now from the law of ideal gas, you can see that PV equal to nRT. Now in this experiment, I will try to increase the volume of this balloon by increasing its mole. And by increasing its mole, I mean to blow into it. Now from the start, it barely has volume. Now it has volume, which means I increase the mole and the volume. Now you can see there's two balloons. This is the balloon I blow before the video. This is the balloon I blow inside the video. As you can see, the balloon I blow before the video is bigger, therefore it has more mole.
The second one is Boyle's law. In the simulation, we could see that when the volume decreases, gas molecules collide more often and pressure increase. But if the volume increase, gas molecules are rarely collide with each other, which make pressure decrease. Therefore, Boyle's law shows us that the pressure is inversely proportional to the volume.
So in this experiment, we're gonna be changing the volume so that we can change the pressure. So we have here a water bottle. So when I squeeze the volume will decrease, so the pressure can increase. When I open the cap, it will shoot forward, so that means that the pressure is increasing.
Cool. The third one is Charles' law.
Charles' law states that the volume of a gas is directly proportional to its absolute temperature, assuming the quantity of gas and pressure remain constant.
Okay, so for today's experiment, we are going to test that when we increase the temperature, the volume also increase just like this one. And to showcase this experiment, we have a lighter, a candle, and also a can of Coca-Cola with a balloon on top of it. So what we want to do is to put the light on the candle and put the can on top of the candle so that we can see that temperature increase, the volume also increase, which make the balloon start to expand bigger and bigger. After that, we want to compress the balloon together, like compress the atoms together by putting it in the water ice bucket. So you'll see it expand, then compress together to the original state like this one. That's it.
Rồi, để tiếp. Tạo kia cho quanh hả? Tạo cho quanh, tạo cho tập liếng room kia mà. Thế. Đã cho nó. Đã cho tập. You know. Watch. Magic. What? It's not. It is. Oh, it is.
Rồi, I protected.
The last one is Gay-Lussac's law. In the simulation, at a constant volume, if we increase temperature, most of the particles move faster and collide against the container wall, which means the pressure also increase. But if we decrease the temperature at a constant volume, most of the particles don't collide against the wall, which make the pressure decrease. Therefore, Gay-Lussac's law tries to show us that P is proportional to temperature. Our indigenous technology today is the Koum, which is closely connected to our traditional customs. We will apply Gay-Lussac's principle in the construction of Koum.
Hot bị đây.
Hột bị đây, để sắp rôn nạn lên đây.
Thank you, boys. Thank you.